In the spring of 1943, Reichsmarschall Hermann Göring, commander of the Luftwaffe, second most powerful man in the Third Reich, was asked by his own staff whether the dams of the Ruhr Valley were vulnerable to aerial attack. His answer was categorical. The Möhne Dam was a masonry gravity structure 34 meters thick at its base, designed to hold 132 million tons of water against every conceivable force. The anti-torpedo netting made underwater approach impossible. The anti-aircraft batteries made low-level attack suicidal. The British did not have a weapon capable of breaching it. This was not speculation. It had been tested. Albert Speer, the Reich's armaments minister, had reached the same conclusion independently 2 years earlier. He had flagged the dams as a potential vulnerability, the only thorough man in the room, and then been reassured, with detailed engineering evidence, that no bomb in the Allied inventory could touch them. He had documented his concern, noted the official reassurance, and moved on to other problems. The German High Command was not negligent. It was not arrogant. It was, by every reasonable measure, correct. What no one in Berlin had calculated for was a 54-year-old aircraft designer in Surrey who had spent 3 years in his study working out why they were wrong. May the 16th, 1943, 28 minutes past midnight, over the black surface of the Möhne Reservoir, Westphalia, a Lancaster bomber is flying at 60 feet above the water, not 60 meters, 60 feet, at 220 miles per hour, in the dark. The trees at the reservoir's edge are level with the cockpit windows. 1 fraction of an inch of wrong pressure on the control column, and 7 men vanish into the reservoir without a trace. Beneath the aircraft, a cylindrical drum the size of a garden roller is spinning backwards, counter to the direction of flight, at 500 revolutions per minute. 3 consecutive air marshals had called this impossible. The Air Ministry had returned the inventor's letters without comment. At 425 yards from the dam wall, the bomb aimer presses the release. The drum drops. It hits the water. Not with an explosion, with a bounce. It bounces again, and a third time. Skipping across the reservoir like a stone thrown at a summer pond, except this stone weighs 9,250 pounds, and it is spinning, and it is carrying 6,600 pounds of high explosive towards the concrete wall that the Reich's own engineers had just finished declaring safe. The cylinder reaches the wall, settles against it, sinks. What Speer did not know, what Göring's engineers had not calculated, was that the water itself would become the weapon, that an explosion at depth, in direct contact with masonry, transmitted through incompressible water with nowhere to go, does not dissipate. It propagates, directly into the foundation, with almost nothing lost. The Möhne Dam, 30 years old, perfectly designed, officially invulnerable, began to crack. The man who designed the bouncing bomb was not a military officer. He was not a government scientist. He was a 54-year-old aircraft designer at a private company who had spent 3 years being told his idea was childish, technically impossible, and a waste of the government's time. His name was Barnes Wallis, and as the Möhne Dam cracked above the black water, he was in an operations room in England with his hands gripping the edge of a table so tightly, by every account, that the knuckles had gone white. This is the story of one man's refusal to accept a rejection letter, one cylinder spinning backwards at 500 revolutions per minute, and 19 bombers flying at the height of a rooftop on the darkest operational night of the war. May 17th, 1943. Operation Chastise. Göring had guaranteed the Ruhr was safe. He was wrong. To understand why the dams mattered, you have to understand what the Ruhr Valley was in 1943. The Ruhr was not simply a region, it was a machine. A purpose-built, historically evolved industrial organism that produced 70% of Germany's steel and 60% of its coal. Every Tiger tank that rolled off a production line, every artillery shell stacked in a Wehrmacht ammunition depot, every pressure hull welded onto every U-boat in every shipyard, all of it began in the Ruhr. The valley had been the heart of German heavy industry since the mid-19th century. By the time the Second World War began, it contained the highest concentration of industrial capacity of any area of equivalent size in Europe. The cities of Essen, Dortmund, Bochum, and Duisburg were connected by an intricate web of railways, canals, and roads, all carrying ore and coal and finished steel in continuous, uninterrupted circulation. Powering all of it was water. The great rivers of the Ruhr, the Möhne, the Ruhr, the Eder, and their tributaries, were the circulatory system of this machine. The factories needed water for cooling. The steam turbines needed water for power generation. The coal mines needed water management to prevent flooding. And 3 dams in the hills above the valley controlled the entire supply. The Möhne Dam was the most important. Built between 1908 and 1913, it was the largest masonry dam in Europe at the time of its completion. Its wall was 650 meters wide at the crest and 34 meters thick at its base. The reservoir it held contained 132 million tons of water at maximum capacity. Draining it, controlling its output over dry summer months, was what allowed the Ruhr's water table to remain stable and its industrial systems to keep running year-round. British Bomber Command had identified the dams as a high-value target as early as 1938. Long before the war began, RAF planners had noted that a successful attack on the Möhne's reservoir could disrupt Ruhr industry far more effectively than any number of direct factory raids. The problem was that every method of attacking it had been tried, in theory if not in practice, and found wanting. Conventional aerial bomb? German engineers had run the calculations. Even a 4,000-pound bomb making a direct hit on the dam crest would produce a cratering effect in the outer surface. The structure beneath, solid masonry, gravity designed to hold 132 million tons of hydrostatic pressure, would absorb the blast with minimal structural consequence. Tests conducted by the German Military Engineering Corps had physically demonstrated this. Bombs had been dropped on test sections. The concrete had cracked and chipped. It had not yielded. Torpedo? The Germans had strung anti-torpedo nets across the entire surface of the Möhne reservoir, 150 meters upstream of the dam face. Any conventional torpedo approaching at the standard operational depth of 10 to 15 meters would detonate against the netting long before it reached the wall. Sabotage divers? The Germans had installed underwater searchlight arrays pointing directly outward from the base of the dam. Anything larger than a trout approaching within 100 meters at night would be illuminated and shot. The underwater defense coverage was complete. And so, by 1940, the official assessment, confirmed by the Luftwaffe's own inspection corps, verified by the Wehrmacht's engineering branch, personally reviewed by Albert Speer, was categorical. The dams were safe. No weapon in the current Allied inventory could threaten them. The infrastructure of the entire Ruhr Valley rested on that assessment. Speer was not complacent. He was accurate. Nothing in the Allied arsenal of 1940 could threaten the Möhne Dam. The critical word was yet. Barnes Neville Wallis was born in 1887 in Ripley, Derbyshire. His father was a doctor who contracted polio after the birth of his second child and spent the remainder of his adult life partially paralyzed. Barnes grew up in a household shaped by stoic endurance of circumstances, the kind of family where problems were not complained about but worked around, where resourcefulness was a moral virtue rather than simply a practical skill. He trained as a marine engineer and joined the airship industry before the First World War. He spent the war years at Vickers designing the hulls of rigid airships for the Royal Naval Air Service. When airships went out of fashion after the war, he adapted. He taught himself aeronautics from first principles. He became, through pure self-directed study and extraordinary innate mathematical ability, one of the most capable structural engineers in British aviation. By the late 1930s, Wallis was chief designer, structures, at Vickers Armstrong's Aviation. His most significant contribution was the geodetic airframe, a revolutionary lattice basket structure made of light alloy that gave aircraft like the Wellington bomber incredible structural integrity. A Wellington could return from a raid with sections of its fuselage shot away, entire control surfaces missing, engine nacelles cracked, and still fly. Because the geodetic structure distributed load so efficiently that no single point of failure could compromise the whole. This was how Barnes-Wallis thought. Not about the single dramatic blow, about structural logic, about where the load flows, about what happens when the system's load path is interrupted at precisely the right point. In the summer of 1940, as the Battle of Britain raged in the skies above southern England, and the British public's attention was fixed on the daily kill counts of Spitfires and Messerschmitts, Wallis was sitting in his study in Effingham, Surrey, working on a paper. He called it "A Note on a Method of Attacking the Axis Powers." It was not a dramatic document. It was a product development paper written in the careful, precise language of an engineer, full of footnotes, load calculations, and hydraulic pressure equations. But its conclusion was striking in its scope. Wallis argued that the most efficient way to damage Germany's war-making capacity was not to bomb individual factories. Factories could be rebuilt, machine tools could be replaced, skilled workers could be retrained. But the infrastructure that the factories depended on, the power, the water, the internal transport networks, was far less replaceable, far more interconnected, and, crucially, far more vulnerable if attacked at precisely the right point. His specific target? The dams. He had calculated the hydroelectric power output of the Möhne, Eder, and Sorpe reservoirs. He had traced the water supply dependencies of the Ruhr factories. He had mapped the railway and canal routes that would be severed if the water in those reservoirs was suddenly released into the valleys below. The conclusion of his calculations was that the destruction of a single large reservoir dam, the Möhne specifically, would cause cascading failures in Ruhr industrial output that no amount of factory bombing could replicate. The problem was how to destroy it. Wallis had studied every conventional approach and found them all wanting. The numbers didn't work. The anti-torpedo nets prevented underwater attack. The concrete mass prevented direct aerial bombing. There was no existing weapon in the Allied inventory, with the combination of penetrating power and proximity to the dam face that the physics required. So he worked backwards from the physics. The question was not, what weapon do we have? The question was, what would the physics of dam destruction actually require? He modeled dam wall failure mathematically. He determined that a charge detonating in direct contact with the outer face of the dam, at a depth of between 30 and 40 feet below the water surface, could create a hydraulic shock sufficient to crack the masonry. The crack, propagating under the sustained hydrostatic pressure of the reservoir, would then widen beyond any possibility of control. But to get that charge to the dam face, past the torpedo nets, past the searchlights, past the defensive guns, required something that did not exist. The idea came from his children. Wallis was at home one afternoon, watching his children skip stones on the garden pond, when something clicked. A spinning object dropped at the right angle onto a flat water surface does not simply sink. The spin stabilizes its flight path. The backspin, rotation counter to the direction of travel, grips the surface on contact and converts forward momentum to controlled skip rather than chaotic splash. The object lands, bounds forward, lands again, progressively losing altitude and speed until it reaches the far side. If the object were large enough, heavy enough, carrying the right explosive charge, and dropped at precisely the right altitude and speed and distance, it could skip over the torpedo nets. It could reach the dam face. And because the backspin would hold the cylinder against the wall as it sank, the explosion would be in direct contact with the masonry at the correct depth. The water itself would become the transmission medium. Incompressible, non-compressible, it would carry every joule of the blast directly into the dam's foundation. Wallis presented his calculations to the Air Ministry in the autumn of 1941. The response was formal, courteous, and completely negative. The letter noted that no existing aircraft could carry a weapon of the required mass. No existing mechanism existed to spin a bomb of that size. The method of maintaining 60-foot altitude over a reservoir at night was not technically feasible. The Air Ministry thanked him for his submission and returned it. Wallis did not file it and move on. He built a model, a rectangular glass tank in his garden filled with water. He dropped small cylinders, weighted and spun by hand, into the tank and filmed the results. The backspin worked exactly as the mathematics predicted. He compiled the film footage into a presentation and sent it to the ministry. The ministry sent it back. He approached the Admiralty independently. He approached the air staff through a different channel. He commissioned a report from an external physicist who confirmed his calculations. He revised his proposal 4 times, addressing each specific objection the ministry had raised. At one point, during a face-to-face meeting with a senior Air Ministry official, he was told directly and without softening that he was pursuing a personal obsession at the expense of the government's time and his own professional credibility. He was 54 years old, the official reminded him. He had a distinguished career. He should not risk it on a fantasy. He was 54 years old. He was running out of time. And he had walked away from that meeting with his hands shaking and gone directly back to his study and revised the proposal a 5th time. The breakthrough came in the spring of 1942, not from the Air Ministry, from the top. Air Chief Marshal Sir Charles Portal, Chief of the Air Staff, received a copy of Wallis's latest proposal through a back channel, not through official submission, but through a personal contact who thought Portal was the kind of officer who would actually read it. Portal read it. Portal was the kind of officer who actually read things. He did not dismiss the mathematics. He forwarded the proposal to Air Marshal Harris at Bomber Command with a note that was unusual for its directness. He wanted to know specifically whether Harris's operational objections were substantive or whether they reflected a general reluctance to devote Lancaster resources to specialized missions. Arthur Harris, Bomber Harris, as he was known to his crews with an affection that masked the reality that he was sending them to die at a rate of approximately 3% per mission, did not like Barnes-Wallis's idea. He found it eccentric. He was deeply skeptical that the tolerances Wallis described were achievable operationally. He used the phrase circus tricks in at least one internal memorandum. But Portal outranked him. And Portal had asked a specific question. A proof of concept test was authorized, full scale. A concrete water tank at the Admiralty's research facility at Teddington, 60 feet long and 6 feet deep, would be used. The test bomb, not yet the final upkeep design, but a full-scale prototype of the cylindrical shape at the right mass, would be dropped by a test aircraft at the specified altitude and speed. Wallis drove to Teddington on the evening of the 23rd of November, 1942. He slept very little that night. By his own account, relayed to his biographer, he lay on his bed in the spare room of a colleague's house and recalculated the primary variables for the 100th time, checking each against the experimental data from the garden tank. He was certain of the physics. He had been certain of the physics for 2 years. Being certain of the physics had not, up to this point, been sufficient. On the 24th of November, 1942, in the presence of 3 Air Ministry observers and an Admiralty liaison officer, Barnes-Wallis's test bomb was dropped from a modified aircraft over the Teddington tank. It skipped 4 times. It struck the far wall directly and cleanly, precisely where the calculations predicted it would. Wallis wrote one word in his laboratory notebook that evening. Not an equation. Not a revised calculation. One word. He wrote, "Works." 4 months later, on the 21st of March, 1943, authorization came through for Operation Chastise. A new squadron would be formed, 617 Squadron, Royal Air Force, based at RAF Scampton in Lincolnshire. The squadron would be given the most experienced Lancaster crews available in Bomber Command. They would be trained for an unspecified precision mission requiring extreme low-level flying capability. They would not be told what the mission was. They would train for 7 weeks. And of the 133 men who would eventually climb into those 19 Lancaster bombers on the night of May the 16th, the majority would spend those 7 weeks training to fly at an altitude that the RAF's own training manuals categorized as unsurvivable in darkness over water. They trained anyway. Wing Commander Guy Penrose Gibson was 24 years old, 24, and had already flown 72 bombing operations over Germany and 101 night fighter sorties. He had been operational, in one capacity or another, since the first week of the war. He had survived things that killed most men in Bomber Command before their 30th mission. The RAF described him officially as an exceptional pilot and an outstanding leader of men. His crews described him differently, depending on which crew you asked. The consistent thread was this: Gibson flew the way a surgeon operates, precise, controlled, no wasted motion, no adjustment made a moment late, and no tolerance whatsoever for imprecision in anyone else. In March of 1943, Gibson was told he was being pulled from frontline operations. He was not told why. He was told only to report to No. 5 Group Headquarters, that his current tour of operations was over, and that he was being given command of a new unit still in formation. He was told 3 things about what the unit would do. The mission required extreme low-level precision flying at night. It was a specialist operation of the highest priority, and his training period would be approximately 2 months. He was not told the target. He was not told the weapon. He was handed a list of aircrew from across Bomber Command and told to select the ones he wanted. Gibson spent 2 weeks making that selection. He went through operational records himself, looking not just at survival statistics, but at the specific types of errors recorded in debrief reports. He was looking for pilots who, under extreme operational stress, kept their aircraft level and their course precise. He was looking for bomb aimers whose release point accuracy was consistently within tight margins. He was looking for navigators who didn't panic when the route became uncertain. He was also looking, though the operational records didn't categorize it this way, for men who could be trusted not to ask too many questions. 617 Squadron, when fully formed, would know for weeks that it was training for something important without knowing what. That required a particular kind of professional discipline. The men Gibson selected came from across Bomber Command: British, Australian, Canadian, New Zealand, American. Several were veterans of 30 or more previous operations. None of them were told why they'd been chosen, where they were going, or why the training they were about to start was unlike anything the RAF had previously attempted. One of the first men Gibson personally called was Flight Lieutenant John Hopgood. They had flown together before. Hopgood was methodical, precise under pressure, and had a gift for understated competence, the kind of pilot you notice not because he does anything spectacular, but because he never makes the small errors that kill people. After every informal squadron gathering, he was the one who organized the mess bill and made sure the junior officers weren't overcharged. Gibson trusted him completely. Hopgood was 21 years old. He accepted the posting without asking what it was for. The training regime began in March of 1943. Its central requirement was simple to describe and grotesque to execute. Pilots had to learn to fly Lancaster bombers at exactly 60 feet above water, at night, at 220 miles per hour, and hold that altitude with enough precision to allow a bomb release accurate to within 2 feet of the required height. At 60 feet, on a still night over a reservoir, the water surface appears almost luminous under moonlight. It is disorienting. The horizon does not behave as it does at operational altitude. The frame of reference the pilot's brain relies on for spatial awareness is simply absent. Everything the vestibular system has learned about flying at altitude is wrong at 60 feet. Several crews nearly died in training. Not from enemy action, from the training itself. One Lancaster on a night exercise in late March pulled up slightly too late after a low run over a reservoir in Wales and struck a power line with its undercarriage. The aircraft shook violently, the undercarriage was damaged, and the crew made it back to Scampton on emergency procedures. The pilot was not removed from the squadron. Gibson personally reviewed the incident, determined the error was marginal and correctable, and put the crew back in the rotation. Another aircraft on a low-level training run over the Derwent Reservoir in the Peak District encountered unexpected turbulence at 60 feet, a function of the reservoir's shape and the wind at that particular angle, and lost 30 feet of altitude in less than a second. The pilot's recovery pulled the aircraft back to 60 feet, with perhaps 20 feet to spare before the water. He did not report the incident formally. He reported it to Gibson privately, and was told to do it again, until it wasn't an occurrence that needed reporting at all. They flew at night, they flew in bad weather, they flew in rain that turned the reservoir surface into a completely featureless texture, where depth perception became zero. They flew until the specific set of physical sensations corresponding to 60 feet at night became, if not comfortable, at least distinguishable from the sensations of 50 feet or 70 feet. Meanwhile, separately from the flying training, Barnes Wallis and his engineering team at Vickers were solving the altitude measurement problem. The Lancaster's standard altimeters were barometric instruments. They measured air pressure differential and converted it to an altitude reading. At altitude, they were accurate enough. At 60 feet, with the ground surface changing constantly and the instrument's natural oscillation, they were not reliable to within the required tolerance of plus or minus 2 feet. Even more fundamentally, the altimeter read height above sea level or above the departure ground elevation, not height above the current surface. Over a reservoir, what mattered was height above the water. If the reservoir level varied by even a few feet from its expected level, the barometric reading was wrong. The solution was almost startlingly simple. 2 Eldis spotlights were mounted on the Lancaster's underside, one beneath the nose, one beneath the tail. Both were angled downward and inward at a precisely calculated angle, so that when the aircraft was flying at exactly 60 feet above a flat horizontal surface, the 2 spots of light on the surface below converged into a figure 8 shape. Higher than 60 feet, the 2 spots were separate, not overlapping. Lower than 60 feet, the overlap increased past the figure 8 into a merged blob. Exactly 60 feet, a clean figure 8. Every time, regardless of the altimeter, regardless of the reservoir level. The physics of the geometry was fixed. When the bomb aimer, lying flat in the Lancaster's nose and looking downward through the perspex panel, saw the 2 circles of light merge into a figure 8 on the surface below, he said one word on the intercom to the pilot. Down. If the 2 circles were still separate. Down. If the overlap was too large. Up. The pilot held on the bomb aimer's voice, not on the instrument, on the words steady, down, up, delivered in real time by a man looking straight at the water beneath them. It was elegant, and it worked. The bomb itself. Upkeep. The cylinder. 60 inches long, 50 inches in diameter, weighing 9,250 pounds. Packed with 6,600 pounds of Torpex explosive, a compound specifically formulated for underwater detonation, 42% more powerful pound for pound than TNT, and engineered to transmit its shockwave through water rather than air. It was not beautiful. It was a squat, blunt-ended drum. Military hardware at its most purely functional. The explosive charge alone was insufficient. Barnes-Wallis's calculations showed that a simple cylinder dropped against the face of the dam would detonate, but most of the blast energy would escape upward and outward. To actually crack masonry of that depth and density required the charge to be at a specific depth, between 30 and 40 feet, in contact with the wall, with the column of water above it acting as a containment medium that forced the shockwave downward and inward rather than up and out. 3 hydrostatic pistols were embedded in the base of the cylinder. These were pressure-sensitive detonators, each calibrated to the atmospheric pressure equivalent of 30 feet of water. All 3 had to trigger simultaneously. If even one misfired, the others would not be enough. The whole system either worked perfectly or not at all. The backspin mechanism was the element that Barnes-Wallis had understood from the beginning, and that had taken the longest to convince anyone else was achievable. The cylinder was mounted in a pair of steel caliper arms, attached to hardpoints beneath the Lancaster's fuselage in the space where the bomb bay had been. A belt drive assembly, powered by the aircraft's hydraulic system, rotated the cylinder backwards, counter to the aircraft's direction of flight, at 500 revolutions per minute. The caliper arms had to hold the cylinder rigidly against the torque of that rotation until the exact moment of release, then release it cleanly without imparting sideways deviation. The tolerances were measured in thousandths of an inch. The engineering team at Vickers built the belt drive and caliper assembly from scratch in 6 weeks, under wartime production conditions, in a factory that was simultaneously producing other aircraft components in higher volume. They could not use off-the-shelf industrial components. None existed at the right specifications. Everything had to be designed, machined, tested, and fitted. It worked first time. Think of it like a billiard player hitting a cue ball with heavy backspin. When the ball strikes the target, instead of transferring its momentum forward and rolling on, it grips the surface and checks itself, the backspin fighting against the forward motion, bleeding speed in a controlled, predictable way. A ball with no spin would carom off at an unpredictable angle. A ball with calculated backspin does exactly what the physics demands. The bouncing bomb did the same thing on water. Without backspin, a 9,000-pound cylinder dropped at speed onto a reservoir surface would skip wildly. The first contact angle would determine the departure angle at random, potentially sending the bomb careening sideways into the torpedo netting, or skipping clean over the dam wall, or tumbling end over end. With 500 revolutions per minute of backspin, the cylinder gripped the surface on each contact. It shed speed in a controlled arc. It settled. And when it finally reached the dam face at low remaining velocity, it sank cleanly along the concrete wall rather than floating away from it. The backspin was the difference between a circus trick and a weapon. Wallis had worked out the initial trajectory mathematics using marbles in a garden pond and refined them with scale models in the Teddington water tank. The final drop parameters, 60 feet, 220 miles per hour, 425 yards from the target, were the result of approximately 2 years of iterative calculation. The margin of tolerance on each parameter was narrow. Altitude, plus or minus 2 feet. Speed, plus or minus 4 miles per hour. Release distance, plus or minus 25 yards. Outside those margins, the bomb either failed to skip cleanly, skipped over the dam, or came to rest against the torpedo nets rather than the wall. The release distance problem was solved by a device that was, in comparison to everything else involved, almost insultingly simple. A Y-shaped piece of plywood, roughly the size of a dinner plate, with 2 nails at the tips of the Y's arms. The bond aimer held this up to the perspex nose panel of the Lancaster. The 2 towers of the Möhne Dam, whose separation was precisely known, subtended a specific angle in the bomb aimer's visual field at exactly 425 yards. When the 2 towers each aligned with one of the nails, release. That was the aiming device for a 9,000-pound bomb being dropped from a Lancaster flying at suicidal altitude in the dark at 220 miles per hour toward a concrete dam protected by 8 anti-aircraft guns, a piece of plywood, and 2 nails. The bomb aimers practiced with the wooden sight obsessively. They took photographs of the dam towers from reconnaissance images and practiced the visual alignment until the movement, see the alignment, press the release, was as automatic as an eye blink. The complete operational requirement, when stated as a list, reads like a mathematical impossibility. Altitude 60 feet plus or minus 2 feet. Speed 220 miles per hour plus or minus 4 miles per hour. Release distance 425 yards plus or minus 25. Backspin 500 revolutions per minute. Detonation depth 30 to 40 feet. All parameters simultaneous, all exact. Every variable had to be correct at once. Not approximately correct, exactly correct. In the dark, at low level, under fire, over a target defended by 8 gun positions whose crews had been briefed that an attack might come and had been at heightened readiness for 3 weeks. May the 15th, 1943. Evening. At RAF Scampton, all aircrew of 617 Squadron were called to the main briefing room. The doors were closed and a sentry was posted. For the first time since the squadron's formation, they were told what they had trained to do. Gibson stood at the front, before a large map of the Ruhr Valley, a cross-section diagram of the Möhne Dam, and a scale model of the target. He explained the upkeep bomb. He explained the convergence spotlights, the wooden Y-sight, the altitude requirements, the speed requirements, the backspin. He explained the 3 targets in order of priority: Möhne, then Eder, then Sorpe. He told them the routing. 2 waves would approach from different directions to confuse German radar plotting. They would fly at 60 feet from the Dutch coast, all the way to the target, to stay below the radar horizon. The first wave, the main attacking force, would strike the Möhne first, then redirect to the Eder with whatever upkeeps remained. He told them the weather window. Heavy scattered cloud was expected over parts of the route, clearing over the Ruhr. Moonlight would be the primary illumination. They would navigate by visual landmarks, railways, rivers, roads, identified at 60 feet during the approach. He told them what the flak positions were. He told them how many guns were on the Möhne Dam. The room was quiet for a long time after the briefing ended. Flight Lieutenant Hopgood, who would not survive the night, was observed by at least 2 other officers during the informal period after the briefing, standing very still by himself near one of the windows, his hands in his trouser pockets, looking at the floor. He did not speak for several minutes. Then he went and got a cup of tea and rejoined the conversation. Flight Sergeant Trevor Roper, the rear gunner of Gibson's own aircraft, wrote in a letter to his sister, a letter that was held by the RAF censor until after the raid, that he had calculated the odds during the briefing and decided they were poor enough that the calculation was no longer useful and that he had stopped doing it. Through the afternoon of May the 16th, the ground crews worked. They checked fuel. They verified the caliper arm release mechanisms on each upkeep. They confirmed the backspin motor hydraulic pressures. They tested the convergence spotlights against a chalk mark on the hangar floor at the calibrated distance. They did every check twice. The upkeep cylinders sat on their trolleys in the dispersal bays, enormous and blunt, looking not like weapons but like industrial components awaiting installation, which, in a way, was exactly what they were. At 21:14 on the evening of May the 16th, 1943, Gibson walked out to his aircraft. His crew joined him at the dispersal bay. The pre-flight checks ran in the order they always ran. The engines were started in the sequence they were always started. The Lancaster taxied to the runway in the position it was assigned. At 21:28, the first Lancaster of 617 Squadron began its takeoff run. 19 aircraft followed over the next 90 minutes. Not all at once. The two waves departed separately, timed to arrive at the target from different approach vectors. They climbed just far enough to cross the English coast safely. Then they began to descend. Down to 200 feet over the North Sea, down to 100 feet as the Dutch coast approached. And then, as the first flak began to rise from the Dutch coastal defenses, and the German radar operators began to notice the oddness of contacts moving too fast and too low to plot coherently, all the way down. 60 feet, over occupied Europe, in moonlight. The trees at the edge of the Dutch farmland were visible at cockpit height. A German soldier standing in a field could have looked the Lancaster pilots in the eye as they passed. Power lines and low-strung telegraph cables were not obstacles visible on navigation charts, but physical hazards requiring sudden violent pull-ups and immediate returns to 60 feet. They flew south and east, toward the Ruhr, toward the dams, toward the dark. 00:28 hours. May the 17th, 1943. The Möhne Reservoir, Westphalia, Germany. Gibson's Lancaster arrived at the target area first, banking low around the eastern end of the reservoir and running straight toward the dam at 60 feet to assess the defenses before committing any bomb carrier to an attack run. He needed to see exactly where the anti-aircraft guns were positioned, measure the quality of the searchlight coverage, and determine whether the approach angle he'd planned from the reconnaissance photographs was actually viable at night in real conditions. The dam was larger up close than photographs had made it appear. This was something almost every crew who survived that night would later comment on separately. The Möhne's scale was not emotionally legible from aerial photographs in the way it was from 60 feet above the water 50 yards away. It was a wall, a real wall. 34 meters of solid masonry reflecting moonlight in a way that created the momentary irrational conviction that it was moving toward you rather than you toward it. 8 anti-aircraft guns opened on Gibson's Lancaster almost immediately. The tracers came in flat, horizontal streams, not the arcing trajectories you see in newsreel footage of altitude bombing, but straight horizontal lines at cockpit height, because the gun crews were shooting at an aircraft at their own level. Gibson pulled up over the crest, banked away to the left, and circled high enough to regroup and broadcast his assessment to the other aircraft circling outside the target perimeter. The defenses were exactly where the reconnaissance had shown them. The approach was viable. The attack would proceed. He briefed the first bomb carrier on the radio. Flight Lieutenant Hopgood. Aircraft M for Mother, 7-man crew. Hopgood was one of Gibson's closest friends in the squadron. He had bought the beer at the post-selection party when the squadron was first formed. He was 21 years old. Before Hopgood ran in, Gibson made another approach himself, deliberately absorbing more anti-aircraft fire, crossing the dam at low level from one side to draw the gunners' attention and tracking, then pulling up and away to force them to reacquire. He had decided, without being ordered to, that he would fly alongside every attacking aircraft during its bomb run, offset slightly so the gunners had 2 targets to track, which would have their accuracy against each. It was, by any standard, an act of extraordinary courage. It was also tactically rational. Gibson was a man who tended to express courage in the form of tactical rationality, which may be why the RAF trusted him with this mission. Hopgood ran in. His aircraft was hit during the approach, one engine nacelle caught fire, and the hydraulic system controlling the upkeep-release arm was partially damaged. The bomb was released, but the release was fractionally late. The cylinder left the aircraft at the right altitude and the right speed, but at the wrong distance. Instead of 425 yards, it was released at approximately 500 yards. It skipped correctly. It cleared the dam crest, and it exploded at the powerhouse building on the far valley side, obliterating the structure but doing nothing to the dam itself. Hopgood attempted to climb to allow his crew to bail out. He had perhaps 60 or 90 seconds of controlled flight left in the damaged aircraft. 2 of his 7 crew made it out and survived. The aircraft exploded at low altitude. Hopgood did not escape. He was 21 years old. The third run was Flight Lieutenant H.B. Martin's aircraft. Gibson flew alongside him the whole approach, close enough for the gunners to have to choose. Martin's bomb was released correctly. It skipped, hit the wall, sank, detonated. A column of water rose above the crest, 60 feet or more, and collapsed back into the reservoir. The masonry cracked, but the dam held. Squadron leader Melvin Young ran in fourth. Young was methodical. His crews called him Dinghy Young because he had survived ditching his aircraft in the sea twice in previous operations and had both times deployed his life raft and been recovered. He was not a man who wasted emotional energy on outcomes he could not control. His bomb skipped correctly, detonated correctly. The crack that Martin's bomb had started propagated downward. A section of the upper crest appeared to sag. The dam held. Gibson was burning through upkeeps. He had 8 to work with on the Myrna. 2 had been expended. 1 wasted on Hopgood's late release, 1 by Martin, 1 by Young. Each had hit the wall precisely and hadn't broken through. Flight Lieutenant David Maltby was 5th. Maltby's bombing record in training had been consistently the most accurate in the squadron, not dramatically, not boastfully, just consistently by the metrics Gibson had used to select the crews. His bomb aimer was also experienced, calm under operational conditions, and had practiced the Y-sight alignment until he could do it in his sleep. Maltby ran in at 11 minutes past midnight. The upkeep cylinder spun at 500 revolutions per minute beneath the aircraft as they crossed the reservoir at 60 feet, the 2 convergence spots merging into a perfect figure 8 on the water below. The wall rose toward them. The bomb aimer's eye was at the sight. The towers aligned. Release. The cylinder skipped 4 times, a clean, slightly shorter pattern than the previous drops, which meant it was releasing the right amount of energy on each contact. It struck the wall slightly left of center and sank. Gibson, circling alongside at the same altitude, watched the detonation column rise. For a moment, nothing. The same detonation column. The same white foam. The same sensation, for everyone in the aircraft, looking at the wall from 60 feet, that the concrete was simply absorbing everything they could throw at it. Then a sound that nobody has ever found adequate words for. Not an explosion, a structural sound. Low, geological. 130 meters of the Myrna Dam wall, a section beginning slightly left of center and extending to within 40 meters of the left bank, ceased to exist. 132 million tons of water began to move. The initial flow rate through the breach was approximately 200 cubic meters per second. Within minutes, as the collapsing masonry widened the gap, it exceeded 800 cubic meters per second. The water velocity at the breach face exceeded 80 miles per hour. Gibson's radio operator sent the code word back to Bomber Command headquarters in England. nigger. The agreed signal that the Muna had been breached. In the operations room at High Wycombe, Barnes Wallis, standing beside the duty signals officer, heard the word come through the receiver. He turned away from the room for a moment. Several people who were present later said they believed he was crying, though he denied this afterward. He described it as a momentary loss of composure. Given that he had been working toward this moment for 3 years, and being told it was impossible for 2 of them, the distinction between crying and a momentary loss of composure may not be meaningful. The remaining aircraft with unspent upkeeps were redirected immediately. They climbed, turned east, and flew for the Oder. The Eder Dam was in some ways a more difficult target than the Möhne, precisely because the Germans had not fortified it as heavily. The Möhne had been defended because the Germans knew it was a potential target. They had studied the same calculus British planners had studied and reached the same conclusion about its strategic importance. They had put 8 heavy anti-aircraft guns on it and strung torpedo nets across the reservoir. The Eder had no such defenses. The reason was the approach geometry. The reservoir was long and narrow, set in a deep valley with steep forested hillsides, rising sharply on both sides. To attack the Eder Dam from the water, an aircraft had to approach from the western end of the reservoir, which required flying over a sharp ridge, descending steeply into the valley, leveling off at 60 feet on the reservoir surface, and making the bomb run, all within approximately 12 to 15 seconds of crossing the ridge. German planners had looked at this geometry and concluded that no bomber pilot could accomplish the maneuver with adequate control. The approach was too tight, the descent too steep, the time between ridge and bomb release too short. The Eder was naturally protected by its geography. They were nearly right. The first 3 approach runs by the attacking Lancasters had to be abandoned. Not because of flak. There was no flak. Because the approach geometry was exactly as difficult as the Germans had calculated. Getting a Lancaster over the ridge at the correct airspeed, established on a 60-foot run with the correct stabilized speed before reaching the release point, required a sequence of maneuvers that had to be executed almost perfectly within a compressed time frame. The problem was that each failed approach required a full go-around, back over the ridge, a wide circuit, repositioning for the next attempt, and each go-around took time. Time that burned fuel, time that increased fatigue, time that German radar operators were using to establish a more coherent picture of what was happening in the Ruhr. Squadron leader Maudslay, 21 years old, Gibson's deputy in the first wave, made his first approach and had to pull off. Second approach, same. Third approach, the bomb was released, but the release was fractionally late. The upkeep struck the crest of the dam rather than the water face. The detonation was almost directly beneath Maudslay's Lancaster as it crossed the wall. The aircraft shook. Observers watching from outside described it as the aircraft staggering sideways in the air as though something had physically struck it from below. A garbled transmission was received from Maudslay's aircraft on the radio. The exact words were not decoded clearly enough to transcribe. Maudslay turned the Lancaster north, toward England. He was shot down by light anti-aircraft fire near Emmerich, on the Dutch border, approximately 90 minutes later. None of his crew survived. He was 21 years old. Pilot Officer Les Knight, an Australian, 22 years old, flying his first operational mission with 617 Squadron, made his approach on the 4th attempt of the Eder attack. His bomb aimer was Sergeant Ray Johnson. Knight flew the circuit back over the ridge so precisely at exactly the right engine settings that the final descent brought him to 60 feet above the reservoir surface with 50 yards to spare before the optimal release point. Johnson had the Y sight to the nose panel. The towers aligned. He pressed the release. The cylinder bounced cleanly. 3 skips. It hit the wall slightly to the right of center, settled against the concrete, and sank. The detonation column was slightly different from the Möhne's. The Ader's geometry concentrated the shockwave differently. The crack propagated down 60 meters of the wall face in under 2 seconds. Then the wall shifted. Then the Eder Dam gave way. 2 dams, 150 million tons of combined water in the same night. The signal went back. Dinghy. The Eder was breached. Back in England, Barnes-Wallis received the second code word. This time, by multiple accounts, he did not try to maintain composure at all. What happened in the valleys below the breached dams between midnight and dawn on May the 17th is difficult to enumerate in the way that military historians prefer to enumerate things, because it happened too fast and in too many places simultaneously. The flood wave from the Möhne traveled at 15 miles per hour on average in the open valley sections. But in the narrower gorges downstream, where the valley walls compressed the flow, it accelerated to 2 or 3 times that speed. The wavefront was, by the accounts of the few surviving eyewitnesses who saw it from high ground, not a running wave, but a wall. A moving wall of dark water carrying farm machinery, roof timbers, haystacks, and the structural remnants of every bridge it had hit. Every road bridge in the first 25 miles downstream of the Möhne was destroyed within the first 2 hours. Every railway bridge, every telephone exchange, every power substation in the flood corridor went offline simultaneously because the transformers were either submerged or the cable routes crossing the valley were severed. The hydroelectric generating capacity of the Ruhr Valley fell to approximately 30% of normal output that night and remained below 50% for weeks. Steel mills that operated continuous electric arc furnaces had to shut down, not because the mills themselves were damaged, but because the power simply was not there. Coal mines in the flood corridor stopped pumping. Some did not restart for months. Albert Speer, who was pulled out of bed by a telephone call from his ministry at 3 in the morning and driven to the Ruhr by staff car, arrived at the Möhne Valley 6 hours after the breach. He stood on the high ground above the valley floor and looked at what the water had done to the landscape below him. By his own account in his post-war memoirs, he was unable to speak for several minutes. He was, also in his own account, thinking about the forced labor camps. Approximately 1,200 people were killed in the Möhne and Eder floods. Of those, the majority, over 1,000, were not German civilians. They were Soviet and Ukrainian workers, predominantly women, who had been housed in labor camps in the valley downstream of the Möhne Dam. The camp had been established precisely because the valley floor was flat, well-drained in normal conditions, and far enough from urban centers to keep the workers isolated. The same geography that made it a sensible location for a forced labor camp made it a perfect channel for a flood wave. The women in the camp had no warning. There was no siren system in the valley for this scenario. A guard at the camp perimeter was the first person downstream to hear something, a sound he initially compared, in the subsequent investigation, to distant thunder. By the time the meaning of that sound was understood, the flood was 2 minutes away. Barnes-Wallis knew there were civilians in the Ruhr Valley before the raid was authorized. Bomber Command knew it. The Air Ministry knew it. The casualty projections had been calculated, not specifically, not with the precision that would identify a camp of female forced laborers in a particular valley. But in aggregate terms, the planners had estimated probable civilian deaths in the flood corridor and weighed them against the strategic value of the dams. The decision to proceed had been made. It was made by men sitting in offices in England who did not see the valley. It was carried out by men in Lancaster cockpits who were traveling too fast at 60 feet to see anything below them clearly. And it killed over 1,000 people who had been transported to that valley against their will by the same government whose military infrastructure the operation was designed to destroy. Whether the calculation was correct has not been resolved. It has simply been deferred. Of the 19 Lancaster bombers that left RAF Scampton on the night of May the 16th, 8 did not return. That was a loss rate of 42%, more than 4 times the average Bomber Command loss rate for a normal operation, and more than double the rate at which Bomber Command considered a target prohibitively expensive. 53 men killed, 3 taken prisoner, 77 returned. The losses were not random. They were concentrated in the aircraft that had to fly the most exposed approach routes at the lowest altitudes against targets that had more time to bring their defenses to bear. The aircraft lost on the outward route, hit by light flak over Holland or Germany at 60 feet, where the normal evasive action of a Lancaster was simply not available, accounted for 3 of the 8. The aircraft lost on the return when exhausted crews were trying to maintain 60-foot altitude after 5 or more hours of continuous stress, accounted for 2 more. 3 were lost in the attack itself. Hopgood at the Möhne, Maudsley at the Ader, 1 additional aircraft on the Sorpe attack that was hit while making a low pass over that dam, which required a different attack technique, a low continuous run along the crest rather than the skip bombing approach, and which was consequently exposed to defensive fire for a longer period. The Sorpe Dam, the 3rd primary target, and the one that could have made the operation truly decisive, was not breached. The Sorpe was different in construction from both the Möhne and the Ader. It was not a masonry gravity dam. It was an earthen embankment, a massive sloping mound of compacted earth and clay with a concrete core running through its center. That distinction mattered enormously. The skip bombing technique worked against a vertical masonry face because the cylinder could settle flat against the concrete and transmit its shockwave through the wall. Against a sloped earthen face, the cylinder skipped up the slope and detonated in the wrong geometry relative to the core. The solution for the Sorpe was a completely different attack method, a low, straight, continuous run directly along the crest of the dam. Not a skip bomb approach, but a near-contact drop from directly above, aimed at the thin concrete spine inside the earthen mound. The Lancaster had to approach along the dam's length rather than perpendicular to it, exposed to any fire for far longer, with none of the skip bombing trajectory advantage. 5 aircraft had been assigned to the Sorpe. 3 were lost on the route or turned back with mechanical failures before reaching the target. Of the 2 that reached it, 1 dropped but failed to breach. The Sorpe cracked on the face, but its earthen mass absorbed the shockwave without catastrophic failure. This is the number you carry away from Operation Chastise when you think about what was actually at stake. The Ruhr's water supply was managed by those 3 dams in a system. The Möhne and the Eder were breached. Had the Sorpe also been breached, the combined flood would have been on a scale that no repair program launched within a war could have addressed in anything under a year. The Ruhr's output would not have fallen 3 to 7%. The estimates, on the high end, ran to total industrial paralysis for 6 to 9 months. The Sorpe held. Speer repaired the Möhne in 4 months. The industrial disruption was real but survivable. Of the 5 crews assigned to the Sorpe, the 2 that reached it both turned for home in the pre-dawn darkness, their upkeeps either spent or still aboard. Neither crew was certain, in the dark and confusion, quite what they had achieved. Neither crew knew at that moment that the dam was still standing. It was. The strategic assessment that followed the raid was more complicated than the immediate headlines suggested. The losses in industrial output were real but temporary. Albert Speer, who was, whatever his role in the Nazi system, an extraordinary administrator, mobilized 7,000 repair workers within 48 hours. He pulled them from the Atlantic Wall construction program in France, which was a significant diversion of resources, but he had the Möhne Dam repaired and the reservoir refilled to operational levels by the end of September 1943, approximately 4 months. The direct industrial disruption, power outages, flooded mines, broken transport links, cost the Ruhr Valley between 3 and 7% of its annual industrial output for the period following the raid, depending on how the accountants did the calculation. That was real damage. In absolute terms, it was not decisive. What Speer's productivity metrics did not capture, what productivity metrics are structurally incapable of capturing, was the effect on German confidence in the invulnerability of its industrial infrastructure. Before May the 17th, the dams were safe. Germany's planners knew they were safe. The calculations had been done, the defenses installed, the assessments reviewed. The dams were safe. After May the 17th, nothing was safe. If the dams could be attacked, what could not? Albert Speer spent the next 2 years of the war deploying anti-aircraft defenses to facilities and infrastructure nodes that had previously been considered immune from aerial attack. That deployment absorbed resources, manpower, and planning capacity that would otherwise have been used for offensive production. The bouncing bomb's long-term effect on Germany's war economy was not the flood. It was what the flood proved was possible. Barnes Wallis went on. He designed the Tallboy bomb, a 12,000-pound deep penetration weapon with a hardened steel nose and a supersonic terminal velocity, engineered to enter the Earth beside a hardened target and detonate underground, causing a subsurface earthquake that would collapse the structure's foundations from beneath. It could penetrate 30 feet of reinforced concrete. The Tallboy was used to sink the Torpex, which had finally been cornered at Tromsø in Norway. 3 direct hits in November 1944 caused the battleship to capsize, the target that the whole of Operation Chastise had been conceived to deny from the outset. The single dry dock in France capable of servicing the Torpex, the reason the Möhne Dam was attacked, the reason Barnes Wallis had been sitting in his study in 1940 writing equations about dam collapse. That target was now irrelevant because the Torpex was at the bottom of a Norwegian fjord. He also designed the Grand Slam, 22,000 pounds, the largest conventional bomb used in combat in the war. It was dropped by Lancasters of 617 Squadron on the Bielefeld Railway Viaduct in March 1945. The viaduct, which had survived every previous attempt at destruction, collapsed in 60 seconds. 617 Squadron survived the war. Its members were disproportionately decorated, the highest concentration of Victoria Crosses, Distinguished Service Orders, and Distinguished Flying Crosses of any single RAF squadron. Guy Gibson was awarded the Victoria Cross for Operation Chastise. He was killed in September 1944, returning from a raid on Reit, Germany, in a de Havilland Mosquito. The cause was never conclusively determined, probable engine failure or fuel exhaustion over the Netherlands. He was 26 years old. Barnes Wallis never stopped working. He continued as a designer at Vickers after the war, moving into supersonic aircraft research, variable geometry wings, concepts that would eventually, decades later, become the basis for the swing-wing combat aircraft used by several air forces. He received a knighthood in 1968. In interviews conducted in his late life, he was consistently reluctant to discuss Operation Chastise in triumphalist terms. He would speak about the physics. He would speak about Barnes Wallis, the engineer, about the problem of the dams, about the mathematics of water compression. He did not speak with ease about the 53 men who had died executing what he had designed. "I had no idea," he said once, in an interview recorded in the late 1960s, "that it was going to be so costly. That has always been with me. The Möhne Dam was repaired with the same gray limestone masonry used in its original construction in 1913. If you visit the dam today, you can see the seam, a slightly different tone in the masonry, a subtly different texture in the facing stone, running across a 130-meter section of the wall. You have to know what you're looking at to see it. The Eder Dam was repaired similarly. Both reservoirs are currently full. Both generate hydroelectric power for the local grid. Boats sail on the Möhne Reservoir on summer weekends. There is a visitor center on the dam crest. The photographs taken from the dam show a peaceful lake, a forested valley, a blue sky. It is ordinary. It is quiet. The Commonwealth War Graves Commission maintains the graves of the 53 men of 617 Squadron who were killed on Operation Chastise. They are distributed across several cemeteries in the Netherlands and Germany. Most of the men who are buried there are buried near where their aircraft came down, near the field or the ditch or the reservoir where an aircraft traveling at 60 feet in the dark simply ran out of altitude at the wrong moment, and that was the end. Local communities near many of those graves have maintained them continuously, without prompting from the Commission. Flowers appear on certain graves in mid-May, on the anniversary. The people who leave the flowers are, in most cases, not British. They are Dutch. They are German. They are people who did not choose to be near a military objective in 1943. They maintain the graves because they understand, in the way that proximity to specific history teaches you to understand, that the men buried there were not abstractions. They were 21, 22, 23 years old. They flew at 60 feet in the dark because someone had correctly calculated that this was the right thing to do. 19 Lancasters, 133 men, 8 aircraft lost, 2 dams breached, 1 dam held, 53 dead, 1 cylinder of Torpex, spinning backwards at 500 revolutions per minute, carried at the precise speed, at the precise altitude, released at the precise distance, by a man looking through a Y-shaped piece of plywood at 2 towers in the moonlight. Go to the Möhne Dam today. Stand on the crest. Look at the masonry. There is a seam in the stone that runs for 130 meters across the middle section of the wall. A slightly different tone. A subtly different texture. A repair made in the summer of 1943 by 7,000 workers under Albert Speer, in 4 months, under wartime conditions, because the Reich needed the water back. To see the seam, you have to know where to look. Barnes Wallis knew where to look. He had spent 3 years working it out. And it took 19 Lancaster bombers, 133 men, and 53 of them not coming home, to prove that he was right. 1943. The dams were going to be safe forever. Until the night a man who had been told no for 3 years sent a stone skipping across a pond.